So we've talked about the big ideas of limits and derivatives quite a bit, and now we're going to bring up the third big idea that we talk about in calculus a lot, and that is antiderivatives or integration. So the way we'll start this conversation is by looking at something that's familiar to us, the derivative of x squared. So the derivative with respect to x of x squared. We know that this is 2x. Now, when we're talking about this derivative of x squared is equal to 2x, this value of 2x is referred to as the derivative. Well, what is x squared referred to? X squared is referred to as the antiderivative. Now what we want to do when we start working with these problems is we want to start looking for patterns and kind of thinking backwards. So the derivative with respect to x of what, we want to fill in the blank here, is equal to 3x. So I kind of have to reverse what we're looking at here. So the question is, what did I take the derivative of to get to 3x? Okay, well if we start guessing, one guess could be, I don't know, maybe it was the derivative with respect to x of 3x squared. Actually just do x cubed, because I know that that 3 has to come out front. When I take the derivative, I get 3x squared. So, nope, this isn't correct. I wanted 3x. So let's try another guess. So the derivative with respect to x of, I know I need a 1 here. And so when I decrease my exponent by 1, I must have had a 2 here to begin with. So maybe let's try 3x squared. So the derivative of 3x squared would be 6x, and that's not right either, but it's closer and my power is correct. Now if this if this 6x was just divided by 2, I would have it. So again, we're just kind of going through this with the process of elimination, trying to come up with the correct antiderivative. So I think it's going to be 3/2 x squared. When I bring the 2 down and decrease my exponent by 1, the 2's cancel and I'm left with 3x, and this checks. So my antiderivative right here was 3x. But the question is, was that the only antiderivative that it could have been? Now that I'm on the right track, let's guess again. What about the derivative with respect to x of 3/2 x squared plus 4, let's say? Well, we already know if we bring the 2 down, the 2's cancel and I'm left with 3x, and the derivative of a constant is 0, so this is right as well. Okay, let's guess again. So again, we're looking for these patterns. What if this was a minus 7? The derivative, I bring the 2 down, the 2's cancel, and I'm left with 3x. The derivative of a negative 7 is 0. So this checks as well. So I'm kind of thinking that as long as this variable piece is there, this 3/2 x squared, it doesn't matter what this constant is that I have, it's going to give me a derivative equal to 3x. So the way that we represent this then is we're going to call this 3x plus c, where c represents any constant. So that's the pattern that I need to start thinking of. That's what I want to start looking at. Not just 3x, but an entire family of functions of 3x with any constant added to it. So the antiderivative here is 3/2 x squared plus c. So I filled in the wrong blank there. So 3/2 x squared plus c. So that's my antiderivative. When my derivative is equal to 3x. So again, we want to start looking at these patterns and trying to look at trends and coming up with the antiderivative. Now there's easier ways to do this that we'll learn in a little bit called the power rule, but we want to be able to think backward and look for those patterns. It's going to be very, very important. Now originally when we would start working some of these story problems, we would be given a position function and the position function was given as s of t. And we would take the derivative of the position function to get the velocity function. So this is velocity. And we would take the derivative of the velocity function to get acceleration. So acceleration would be equal to the derivative of v, which is the second derivative of the position function. So this process is pretty easy to look at: position, velocity, acceleration, derivatives. But the question is, what if you weren't given position? What if you were given acceleration? What would we do? So what if you're given acceleration? How would we get to velocity? How would we get to the position function? And we'll look at a problem like this a little bit toward the end of this lecture, but that's one of the things that motivates us, is how do we work things backward if we're given different pieces of information. Now, of course, trig functions are going to come into play here. So let's look at the derivative with respect to x, and again, this is, I'm filling in this blank. The derivative of what is equal to the cosine of x? Well, if you remember all of your trig function derivatives, you know that the derivative of sine is equal to cosine. But there could be any constant added on as well. So the derivative of sine of x is cosine of x. The derivative of a constant is 0. So the way we would say this is the antiderivative of the cosine of x is the sine of x. And we're going to add that plus c. So again, one more time, this is the antiderivative, and the cosine function is my derivative. Now we can check all of these. That's one of the cool things about this particular section, is I can check all of my answers. All I need to do is to take the derivative of my antiderivative, and I better get my derivative back. And let me put that plus c in here. The derivative of sine is cosine. The derivative of a constant is 0. So this does check, and I would always encourage you on your homeworks, handwritten homeworks, quizzes, exams, to always give this double check. Because when I take the derivative of the antiderivative, I should get the derivative back. And again, it's a built-in check. So again, what I'm seeing here is the antiderivative is not unique, because I can add any constant I want to this. So the antiderivative is not unique. So that's why I have this entire family of solutions. So the antiderivative is an entire family of solutions. Unless, of course, some initial conditions are given, and then I can solve for that value of c. So unless some initial conditions are given. And we'll look at some problems where some initial conditions are given, and they're really kind of fun to go back and solve for. And again, one of the nice things about these are you can always take the derivative to check your answers. Now the formal notation that we want to give this is we call cap f the antiderivative. So let's let cap f of x, and again this is a capitalized F, be an antiderivative of lowercase f of x. So this is my derivative, lowercase, uppercase is anti. And it's the antiderivative on some interval, open interval ab. Then what we can say, every other antiderivative on the open interval is of the form cap f of x plus c. And again, c stands for some constant. Okay, so this is a really big idea. Now let's go ahead and look at some examples. And again, we'll learn some shortcut rules, but for now we want to look for patterns. So, for example, let's find two antiderivatives of the function f of x equals, let's do cosine of x. And let's determine the general antiderivative. Okay, so we want to write this out in formal notation. So remember, the derivative with respect to x of the antiderivative is equal to the derivative. Okay, so that's antiderivative is my capital F of x, my lowercase f of x is my derivative. So look, what I'm looking for then is therefore, the three dots in the shape of a triangle is therefore, we want to find some of these f of x's. So what do I take the derivative of to get cosine? Okay, so again, let's go ahead and fill in the blank here if we're not sure what's going on yet. The derivative of what is equal to cosine? Now I think we looked at this up here a little bit ago. Yeah, so we already did this one, so let's make this a little more interesting. Let's make this one a negative cosine. Just make it a little bit more interesting. So, what do I take the derivative of to get a negative cosine? Well, if I take the derivative of sine, I get a positive cosine. So if I take the derivative of a negative sine, I should get a negative cosine. And of course, I could have any constant here that I wanted. So some values that could work here are negative sine of x, and again, always put parentheses around the arguments of your trig function. Plus any number that I want here. It could be positive, it could be negative, it could be a fraction. So I'm going to call, let's say, plus 2 here in this case. But again, that was arbitrary. It could have been any number. Another one that would work is, let's say, a minus 4/5. Could be any number here. So the general antiderivative is negative sine of x plus c. So what we have here are two generic antiderivatives, and then this piece right here is the general antiderivative. So the general antiderivative of the negative cosine of x is negative sine of x plus c. So again, that's what we're looking for, some of those patterns. And the only way that this is going to be easy is if we have memorized those basic trig derivatives. And we'll write all those down here as a review in just a minute. Now, the process that we go through to find antiderivatives is called integration. And so this is our big idea. This is what we're going to be spending the rest of the class on, and what you'll be spending most of like Calc 2 on as well. So the process of finding the antiderivative is called integration. So this idea of integration we use a special symbol for. The symbol is kind of this S shape. So this is called an integral sign. So this is the symbol that we use to represent integration. So this is starting to introduce the idea of the indefinite integral. Now there's two types of integrals that we'll look at. There's definite and indefinite. We're definitely starting with the indefinite. So let's talk about indefinite integrals. Now, because we have an indefinite integral, what that means is we have an entire family of solutions, so that's where we have the plus c involved. So for the indefinite integral, what we have is we are integrating the derivative to get our antiderivative plus our constant of integration. So when we're talking about this symbol, this means the integral of f of x, this is lowercase f of x dx. Dx is called my differential, and we'll explain what that means in a little bit. And this is equal to the antiderivative plus c, which is my constant of integration. So we're kind of running out of room here, so let me write it down again below, and we'll have a little bit more room to write about this. So cap f of x plus c is the general antiderivative. Or now we have another name for it, or indefinite integral of our lowercase f of x, of our derivative. So let's go ahead and write our symbols out again. Integral of cap f of x dx is equal to, I'm sorry, this is lowercase over here. Lowercase f of x dx is equal to cap f of x plus c. So let's name all these pieces. This is our integral sign. This is called our integrand. This is the thing that we're trying to integrate. Dx is called our differential. And this kind of tells me what I'm trying to integrate with respect to. Kind of the idea of a derivative, and when we get into Riemann sums, we'll start talking about how this is the base of rectangles and has quite a bit more to it than that. But for now, we'll just call it the differential. Cap f of x is the antiderivative. And this value of c is our constant of integration. So we have a lot of things going on here, a lot of new things. Now, another thing we want to talk about is that some indefinite integrals can be evaluated by reversing the power rule for finding derivatives, and so that's what we're going to talk about next. So some indefinite integrals can be evaluated by reversing the power rule for finding derivatives. Okay, so let's go ahead and recall what the power rule for finding derivatives was. If I wanted to take the derivative with respect to x, let's say of x to the fourth, I would bring the 4 out front, and then I would decrease the exponent by 1 to get 4x cubed. So that's 4 minus 1. So if I wanted to reverse that, it seems like to me we would need to increase this exponent and not multiply but divide to undo what we've just done. So let's go ahead and look at the power rule for integrals. We're going to be using this a lot. So power rule for integrals, big idea. If I integrate a variable to an exponent with respect to x, what I do is I add 1 to the exponent and divide by the sum. So add 1, divide by the sum, plus my constant of integration. Now this only works for n not equal to -1. That's the only time that this will work, if n does not equal -1. So we'll look at an example why n cannot equal -1 after bit, but for now I want to look at a few examples that work. Now sometimes some of these will need rewriting. So for our first example, let's go ahead and look at x to the 5th dx. So I would add 1, divide by the sum, plus my constant of integration. So that would be x to the 6 over 6 plus c. Now remember, we can check every single one of these, and on your test, some of them you're required to check, so make sure you read the directions carefully. because I want to make sure that you know how to check your solutions. Now the next unit that we're going to work on in Unit 4 will be taking integrals all the time. So it's really important that you get proficient with these integrals and then also get good at checking your solutions. So the way we would check this is we would take the derivative with respect to x of x to the 6 over 6 plus c. So now remember, when I take a derivative, I would bring the 6 down, and I already have a 6 in the denominator, and then I would decrease the exponent by 1, and the derivative of a constant is 0. And when I simplify, I get x to the 5th, which is my integrand. So it checks. So again, take the time to check these. A couple of good things that it does when you check them. First of all, you get to practice your skills at taking derivatives. You get to work with your algebra as well. Let's go ahead and look at the integral of 1 over x to the 10th dx. Got to have the dx there. This will be an important idea a little bit later on. Now, I don't have a rule that says the integral of a quotient or the integral of a product. So I need to rewrite this as in terms of a power rule. And the power rule has a variable to a power. So I need to rewrite this before I can actually integrate it. So I'm going to flip this up top by rewriting this as x to the negative 10 dx. So what we'll do here is we'll add 1, divide by the sum, plus c. Negative 10 plus 1 is negative 9. Negative 10 plus 1 is negative 9 plus c. Now rewriting this, the x to the negative 9 would flip, so I'm left with a negative 1 over 9x to the 9th plus c. That's my solution. That's my integral. 1 over x to the 10th is my integrand, which I rewrote, so I could use the integral power rule. We can go ahead and check our answer here by taking the derivative with respect to x of negative 1 over 9x to the 9th. Now if I wanted to take the derivative of this in the current form, I would have to use the quotient rule, and I don't want to use the quotient rule, so I'm going to go ahead and rewrite this by flipping it back up top into this form. X to the negative 9 over 9, and of course I forgot my plus c in this one, so I'm going to include that. So when I take my derivative, I bring the negative 9 down. Remember, I already have a 9 below. I decrease the exponent by 1, so negative 9 minus 1 is negative 10, and the derivative of a constant is 0. Simplifying this, it looks like the 9's cancel, and then when the 9's cancel, I also have this exponent to work with. Whoops. Up here, this negative is in the denominator. It's flipped up into the numerator, so we're going to have to keep track of that as well. If you notice, when I rewrote this and I flipped the x to the negative 9 up top, I forgot to drag this negative sign along. So this negative sign drags here. And so when I bring the negative 9 down, it becomes a positive 9 because I already have a negative there. The 9's cancel, and I'm left just with x to the negative 10, which is 1 over x to the 10th. And this checks because this is my integrand back. So again, it's really important that you get used to checking your work to make sure that you don't have any mistakes. Now, some of the easiest things to take the integral of are nice polynomial expressions. So when I look at the integral of a polynomial expression, it works pretty slick just to go through and do that quick add 1, divide by the sum. Now, we haven't talked about a constant yet. So, quick rule, add 1, so I'd have 2 plus 1 over 2 plus 1 plus 2x to the 2 plus 1. Actually, we probably better make one of these, let's make this one a constant. 2x to the first, and then 7 will be our constant. So this would be a 1 plus 1 over 1 plus 1, because this is an implied 1, minus 7x to the, right now it's 0. Remember, x to the 0 is 1. 1 times negative 7 is negative 7. So you don't even see the x here. This constant is a constant times x to the 0. So I'm going to add 1 divided by the sum, and of course plus c, my constant of integration. So simplifying, looks like I have 3x to the third over 3 plus 2x squared over 2 minus 7x to the first over 1 plus c. So this would be my integrand. Now again, I can check that by taking the derivative with respect to x. 3x cubed, whoops, I guess I could do a little simplification first. Let's simplify that first. So the 3's cancel, the 2's cancel, and I'm left with x cubed plus x squared minus 7x plus c. So again, reduce and simplify if you can. Now let's go ahead and check it. So I'm taking the derivative of x cubed plus x squared minus 7x plus c. So remember, and you have to keep these straight, it's kind of hard. So when you integrate, you add 1, divide by the sum. When you take the derivative, you bring the exponent down and then decrease it by 1. And the derivative of a constant is 0. So this was my original integrand, so it checks. And again, take the time to check these. Now, we've talked about a couple of important rules here, but we've never really spelled them out. So let's go ahead and have a look. The integral of a plus b is the integral of a plus the integral of b. This would work for the same with subtraction. The integral of a minus the integral, I'll write this out, the integral of a minus b is equal to the integral of a minus the integral of b. So we've kind of used that idea. Also, if we have a constant involved, what ends up happening is I can just drag that constant along. So if I have the integral of a constant times a function, that's just the constant times the integral of the function itself. So these are all true. These are not true. The integral of a product is not the product of the integrals. This is never true. The integral of the quotient is not the quotient of the integrals. So just a quick heads up, these are kind of like the cardinal mistakes that you can make with calculus. On this right side, never do these. These are instances where you'll lose entire credit for a problem. The integral of a product is not the product of the integrals. The integral of a quotient is not the quotient of the integrals. Very important to remember. So we said we'd talk about that one case where I had a power of -1. So let's go ahead and look at that right now. Let's look at the integral of 1 over x dx. Well, the way I'd usually write this is x to the -1, and then I would do my thing of add 1, divide by the sum. And you can see right away here I get x to the 0, which is okay, but what's not okay is the denominator I get 0. So this is undefined. And that means that I can't integrate 1 over x dx using the power rule. I have to have something else to do here with this. And what this comes into play is eventually natural log, but we are not using that natural log or the exponential functions in Calc 1. We'll get into that when we get into Calc 2 a little bit. So we cannot integrate 1 over x dx using the power rule. Now we said we'd review some trig functions, so let's go ahead and look at some basic trig integrals. Now all of these trig integrals are just having x for our arguments. Things would change a bit if our arguments were anything other than x, and we'll look at those examples here after a bit. The derivative of sine is cosine. So this implies that the integral of cosine of x dx is equal to sine of x plus c. And again, put parentheses around the arguments of your trig functions, please. The derivative of the cosine of x is equal to the negative sine of x. So this implies that the integral of the sine of x dx is equal to a negative cosine of x plus c. So what I did is I moved the sine by itself without the negative by either multiplying or dividing by a negative. So the integral of sine is negative cosine. We could talk about the derivative with respect to x of the tangent of x. The derivative of tangent is secant squared of x. So this implies the antiderivative of the secant squared is equal to tangent of x plus c. And again, the plus c implies an entire family of antiderivatives. We can do the same thing for cotangent. The derivative of cotangent is negative cosecant squared of x. This implies that the integral of cosecant squared of x dx then is equal to a negative cotangent of x plus c. Antiderivative. And again, we're making this cosecant squared positive. If we wanted to have this to be negative, then this would be a positive cotangent as my antiderivative. Let's go ahead and look at secant. Get a different color here. The derivative with respect to x of the secant of x is secant x tangent x. That implies that the integral of secant x tangent x dx is equal to secant of x plus c. And again, it's really important that you remember these derivatives, because then you're going to have the antiderivatives down a lot easier. Last one, I think, is the derivative with respect to x of cosecant of x is equal to negative cosecant x cotangent x. So that implies that the integral of cosecant x cotangent of x dx is equal to a negative cosecant of x plus c. So knowing these is really going to save you a lot of time when you start talking about antiderivatives. Now, one thing we really haven't gotten to is, what if the trig function is something other than just x? Okay, so let's go ahead and look at an example where the trig function is something other than x. I'm going to put a big box around this because I think it's very important that you know these. They're going to make things quite a bit easier for you. So let's go ahead and look at the integral, let's say, of the cosine of 7x. Well, we know a few things here. We know from our chart up here that the integral of the cosine is the sine. So I'm thinking that it has something to do with the sine of 7x plus c. But if we go and check this, and I take the derivative of the sine of 7x, I get the cosine of 7x times 7. And of course, the derivative of a constant is 0. So this is wrong. It doesn't check correctly. I have this 7 here that I really don't want. To get rid of that 7, if I divided by 7 here, let's see what would happen. So if I divided by 7 here, the derivative of the sine of 7x over 7 is equal to the cosine of 7x times 7, because that's the derivative, all over 7. And then the 7's would cancel, and then I get the cosine of 7x, and this checks. So it's no longer wrong. So I have to compensate with this in the denominator in order for this antiderivative to work. So that idea of compensation will formalize using use substitution in the next unit, but for now we just kind of want to logic our way through that. On any test or any quiz, make sure that you're keeping in mind, or handwritten homework, that you have to establish and show all of this. You have to show the process. It's going to be very important. Last thing I want to get to is the position, velocity, and acceleration type problems, and then also some problems where we're looking at initial values. Now, when we talk about initial values, we're actually talking about differential equations. So this is just a quick sneak preview of differential equations, which many of you will take. Usually take it after Calc 2 or Calc 3. It usually doesn't matter. So this is an initial value problem. Initial value problems are cool. So what we want to do is solve the initial value problem. And what we mean by solving the initial value problem is we want to come up with the antiderivative. So what we're going to be given here is f prime of x is equal to, let's do something like x squared minus 2x, and we're also given the initial condition then of f of 1 is equal to, let's say, 4. So what we want to do here then is we want to figure out what cap f of x is. So cap f of x is equal to the integral of f prime of x dx. And then we'll apply the given condition. So let's get started with that idea. Cap f of x is equal to the integral of x squared minus 2x dx. So if I integrate, I get x cubed over 3, add 1, divide by the sum, minus 2x squared over 2 plus c. So I have cap f of x is equal to x cubed over 3. The 2's cancel here. So I'm left with a minus x squared plus c. Now we're going to apply our condition to solve for c. So we know that f of 1 is equal to 4. So this is 1 cubed over 3 minus 1 squared plus c equals 4. Okay, so continuing to solve, 1 cubed is 1, so I have 1/3 minus 1 plus c equal 4. I would combine these. 1/3 minus 1 is a negative 2/3 plus c equal 4. I'd add 2/3 across, so I get 4 plus 2/3. That would be the same as common denominator of 3. 3 times 4 is 12, plus 2 is 14/3. So what that's telling me is by solving the initial value problem, I get cap f of x is not a family of solutions, but one specific solution. So that one specific solution would be x cubed over 3 minus x squared plus 14 over 3. And that would be my solution. So again, I'm using that general solution. I'm substituting in my condition to find my particular solution. Now let's get to a problem where we're working with that position, velocity, and acceleration. So for this one, let's talk about a particle moving. So a particle is located at the origin. So a particle is located at the origin at time 0. So before it gets started, it's sitting at the origin. And it begins moving along the x-axis with a velocity v of t equal to 1/2 t squared minus t feet per second. And velocity, correct units, feet per second. Let's let s of t be our position function. And that would be at time t. So if t were 4, then I would want to use s of 4. So the question is, what is the position function? We want to be able to find that. Well, remember, when I had the position function, I had the velocity and acceleration. So position, velocity was the derivative of position. Acceleration was the derivative of velocity, the change in velocity, or the second derivative of our position function. So we're used to starting with position and working down. I need to start at the bottom and work up. So the way I'm going to do that is by integrating. So the way that this works then is the velocity function is equal to the integral of the acceleration function. I don't want an x there, I want a dt. And the position function is the integral of the velocity function. So I can take the derivative down, or I can work with antiderivatives on the way up. So s of t is equal to the integral of v of t dt. So to find s of t, I need to integrate 1/2 t squared minus t dt. So again, when we integrate, we add 1, divide by the sum. So this would be 2 plus 1 over the quantity 2 plus 1 minus t, and this exponent is a 1. So this would be a 1 plus 1 over 1 plus 1 plus c, my constant of integration. So s of t is equal to 2 plus 1 is 3, 3 times 2 is 6. So this looks like 1/6 t cubed minus t squared over 2 plus c. So what we have here then is this is my general position function. Now the only thing I know right now is what's going on at time equals 0. So at time equals 0, your position is at the origin. So what that's telling me is s of 0 equals 0. So that's the condition that I can use here to solve. So I come up here in my position function and I plug in 0. So everywhere I see a t, I'm going to go ahead and plug in that 0. And when I'm all done, this equals 0. So I'm plugging in 0. So this 0 over here comes from my input. The 0 on the end comes from the output. So solving, this goes to 0, this goes to 0, and I'm just ending up with c equals 0. So at t equals 0, the position function has a constant value of 0. So I have s of t equals 1/6 t cubed minus t squared over 2. And that's at t equals 0. So my question is next then, what if we change the initial condition to s of 2 and see what we get from there? So let's change our initial condition. To s of 2 equals 3. So remember, s of t, my general, was 1/6 t cubed minus t squared over 2 plus c. So we're going to use this initial condition. So everywhere that I see a t, I'm going to plug in a 2. So s of 2, and then when I plug those in I should get a 3, and then I'm going to solve for c. So on s of 2, I'm going to get 1/6, 2 cubed is 8, minus 2 squared is 4 over 2, plus c equal 3. So this is 8/6, which is 4/3, minus 2 plus c equal 3. So if I add 2 across, I can do this in a couple steps. I get 5, and then I could subtract 4/3 from each side, and I get c equals 5 minus 4/3. Common denominator there is 3, so I'm going to multiply top and bottom by 3. 3 times 5 is 15, minus 4 is 11, so I get 11/3. So what I have here then is s of 2 is equal to 1/6, actually I don't like how I wrote that, s of t is equal to 1/6 t cubed minus t squared over 2 plus 11/3, given, gosh, I don't even remember what we were given. Oh, that's right, s of 2 equal 3. So I can find a particular value of a function given those particular conditions, and that's a really important thing to be able to do, especially when you're working a lot of these types of story problems. Now I think we've gone over almost all the types of antiderivatives. I want to end with one more. A lot of times you have to rewrite a function in order to be able to integrate it. So let's go ahead and look at an example like 4x to the 4th minus 6x squared all over x. I can't integrate this the way it's written. I can't take the integral of the numerator over the integral of the denominator. Remember, that's a big no-no. So what I need to do is to rewrite this. So this would be the integral of 4x to the fourth over x minus the integral of 6x squared over x dx. Now both of these have a dx on them. Don't drop your dx's. They're very important. Now this is still not ready to integrate. 4x to the fourth over x is 4x cubed dx. And over here, x squared over x is 6x dx. Now I can integrate. So I'm going to add 1. 3 plus 1 is 4 over 4 minus 6x squared over 2. The 4's cancel. 2 goes into 6 3 times. And I'm left with x to the fourth minus 3x squared. And then don't forget your plus c, your constant of integration. Now every problem that we have so far has a plus c on it because we're looking at families of solutions unless we're given initial conditions. Eventually we'll get to definite integrals, and with definite integrals I won't have a constant of integration because I'll have limits of integration. We'll explain that soon, but for right now we don't want to overly focus on it. We want to just think about these ideas of antiderivatives. Good luck on this assignment, and remember, keep the idea of a derivative and an antiderivative straight because they can get a little bit confusing. It's also important to make sure you know the derivatives and the antiderivatives of all of your trig functions. Good luck.